The totient function, or Euler's totient function, is denoted as phi n. It's the number in 1 to n minus 1 that are relatively prime to n. Let's look at an example. We take n equals 12 as an example. We write out all the numbers from 1 to 12 minus 1, in this case 11, and we look at all the numbers and see how many of them are relatively prime to 12. We see that 1 and 12 are relatively prime. 2 and 12 have a common divisor of 2, so we don't circle it. 3 and 12 has a common divisor of 3. 4 and 12 have a common divisor. 5 and 12 are relatively prime, so we circle it. And it goes on. We see that 7 and 11 in this case are also relatively prime to 12. And we see there's 4 relatively prime numbers to 12. So phi 12 is equal to 4. Now, what if the number n is so large that it is not easy if we use this form to write it out and check? Well, it turns out there's a trick. There's a shortcut to do it, which is first we take the n and we do prime factorization and write it down the form. And we multiply the original n with the form 1 minus 1 over prime 1 and times 1 minus 1 over prime 2 and so on. And in this case, we take n equals 12 as an example again. We factorize 12 and it is equals to 2 to the power of 2 times 3. And so the phi 12 is equal to 12 times 1 minus 1 over 2 times 1 minus 1 over 3. And the answer turns out to be 4. And it is exactly the same as if we write it out and check the relatively prime to it. And so this is the shortcut. And well, in cryptography, in RSA algorithm, well, most of the time you'll see that the number n it uses is a product of two primes. In this case, we denote it as n equals p times q. Then this is sort of a special case. And in this case, that phi n is equal to p minus 1 times q minus 1. And we take the example of n equals 6 as an example. It is equal to 2 times 3. So using the p minus 1, q minus 1 equation, we get the answer 2. And by checking it with the original way, we see that it is also 2.